Good afternoon everyone, I am Mr. Ish. Thank you for joining me for this video. Now that we've begun these topics on integral calculus, we are looking here at the concept of integrals and we're understanding it through the lens of this Riemann sums. Riemann sums is not a topic you want to shy away from because it's a very important way of understanding the perspective and the computations that are involved with integral calculus. And it is of my opinion that if you compare the differential calculus with integral calculus ends up being slightly more difficult in terms of computations and in terms of the understanding that is required. But the Riemann sums concept is an easy way to understand the whole concept of integrals. We've presented a basic video on the concept of integral. Now we're just delving some more into this whole idea and topic of Riemann sums. As we go through these Riemann sum videos, you'll understand the importance of having gone through a survey of these topics. Briefly, as a rehash from the previous video, we know we've already established that a integral looks something like this. And you know within this integral we have an integrand which is represented by some function with respect to the independent variable, and it does not necessarily even have to be with regards to x. You could also have a situation such as this arise, and I'm just using different letters c to d. You can have f function with respect to y and dy. It doesn't always have to be with respect to the x-axis. You can have integration with respect to y-axis, but for these initial videos we're looking more so over here. These cases here which will involve function with respect to y and the dy will come more into play when we're looking at areas between curves or volume type of questions. Anyhow, you know this is the lower limit of your integral, lower limit of the interval, the upper limit of the interval. This right here is the function which is being integrated, which is also called the integrand, and this right here represents the independent variable. These are both legitimate forms of integrals. We know from the previous video the Riemann sum concept was something to this extent. Limit as n approached infinity, we were looking at a cumulative effect, a cumulative sum from the first to the nth, and we were looking at the length computation multiplied by the width computation, which was delta x, and you know it's a cumulative sum of the lengths multiplied in the end by a single factor, which was your interval width. But the focus over here is, as you know, right over here. This is what we're eventually aiming towards, the understanding and the computations of this, but we're doing it through this. And then as we go through these videos coming up, we'll get more and more closer to the idea and the use of integrals. When it comes to Riemann sums, as I've told you, there's a specific scheme or template that I've laid out for you. Always start with determination of what your sum is. You have to first see like what are the number of rectangles that are involved or how many intervals which are involved. You know, the larger n values lead to more closer approximations. Right? The more rectangles you can draw, the more closer will be the area under the curve. And Riemann sums does not necessarily have to talk about the area below a curve. It can represent, or it can be a computation which is an area between curves, not necessarily a single curve being involved, but you could have several curves involved and you're looking at the area between the curves, and Riemann sums can be involved in those applications as well. Anyhow, the more rectangles you draw, the more accurate is your area between the curve or area under the curve. And then you also want to look at the delta x, which is your interval width, b minus a over n, representing the width of that Riemann rectangle. Then you want to come up with some sort of sample points. You know you can have left endpoints, you can have midpoints, and you can have right endpoints. These basically represent the sample values which will feed into your function with regards to that sample point, and this will give you your length determination. Then you know you put everything here into this formula and you actually get your area, and we can just say that area with regards to your variable area x. This area x should be a close approximation to a true area which you can compute using integral calculus. And you know, left endpoints, midpoints, and right endpoints can also be, I may not have explicitly stated so, but they can also be given like left corner, midpoint, or right corner, because you know, when you're looking down over here at a Riemann rectangle, you have a left corner right over here and you have a right corner, and then you have this middle edge, the midpoint of this top edge. So you're looking at left endpoint or left corner value, right endpoint, right corner value, and the midpoint value. The midpoint value is the best value to use because it leads to the closer values. Left endpoints lead to under approximations because you end up having dead space. In the right endpoints you have over approximation because you're extending your rectangle beyond the curve. Hence you're adding in more area than you should be, so you have overestimated values. The midpoints have some region of the rectangle above the curve and some region below the curve, so it compensates. Hence you have a closer area determination using this midpoint, and that you should always strive for with the midpoints. So in this video we'll just be looking at some good questions as further practice of these Riemann sum concepts. So let's look at this question over here. We have function which is an exponential one, e to the x, and we have to find the Riemann sum using 5 intervals, or 5 Riemann sums, hence the R5, and we have an interval given 0 to the 1. On the x-axis we have 0 to 1. Essentially we're looking at something which looks in terms of integral form, something like this: 0 to 1 lower limit to the upper limit, e to the x dx. And if you were to calculate this or compute that integral, you could very easily, within a matter of seconds, compute the area below the curve for this function. But you know, we're talking about Riemann sums, so we have to do the more elaborate procedure. And also keep in mind that you could use left endpoints for any Riemann rectangle. You could use the midpoint for a Riemann rectangle, or you can use the right endpoints, but we always strive to use the midpoints because they lead to the more true representation of your area under the curve, because all of this is going to give you your area under the curve. Look here, in the left endpoint you have a significant aspect of the Riemann sum which is below the curve, so you have underestimation. In the right endpoint you have a significant aspect of the rectangle which is above the curve, so you have overestimation of areas. We always want to strive for the midpoints, and that's what we will do in these few questions that we will look at in this video. And I'm going to show you the procedures that I want you to adopt for these Riemann sum type of questions. The first thing you want to do is calculate your n value, because that tells you how many intervals you have, and the calculation involves you just looking right over here. You have n value of 5, and that's all you got to do. The next thing you want to do is calculate your interval width. Delta x is equal to b minus a over n, right? B minus a, 1 minus 0 over n, which is just 1 over 5. So you know each interval is 0.2 units broad. And then let's start making a table. Here's my interval column. This will be my xi column, the sample points, which we know we will adopt using the midpoint. The top edge, the middle of that, should cross the curve. And we're not doing any diagrams, but this is what we're graphically representing here, or what we are graphically thinking about. And then you have a column here, f of xi, as you feed this sample value into this function right over here. Then you know what the formula is. We won't write the formula, but we know the formula. We may write it later on in this question, but right now we won't. So we're starting an interval from 0 to 1, and each interval is 0.2 units. So you know your first is going to be 0 to 0.2. Then the next is 0.2 to 0.4. Then the third is 0.4 to 0.6, then 0.6 to 0.8, and then finally 0.8 to 1.0. The only reason why I'm stressing so much on Riemann sums in this video, and there are 2 more videos coming after this, is because I don't want you to shy from this topic. Since we're using the midpoint values, we have to find the midpoint of each of these intervals. If you're using the left endpoint values, these values right here, this column of values would be your left endpoints. If you were using the right endpoints, these values here would be your right endpoints. But since we're using the midpoint, we have to find the middle of each of these intervals. The middle of 0 and 0.2 is 0.1. 0.2 to 0.4, middle is 0.3. 0.4 to 0.6, the middle of that, or the midpoint of this segment, is 0.5. This is 0.7, and this is 0.9. This next step over here requires you to bring the calculator. You're essentially taking this x values and plugging them in here. So you're looking at e to the 0.1. Here you're looking at e to the 0.3. Here you're looking at e to the 0.5, e to the 0.7, e to the 0.9. And in essence, we can just leave these as our values. This way we don't have to have a cluster of numerals over here with a lot of decimal places. We can avoid all of that. You can look at the cumulative length of all of this, because that will represent your f of xi values, but in a cumulative format. And then you're going to multiply the cumulative sum with this 1 over 5, which is 0.2. Remember the formula: limit as n approaching infinity from the very first to the nth, which would be your 5th term. From your first to the 5th, you have f of xi, the cumulative sum of the lengths, multiplied by delta x. So let's do it. I'm going to run these in a single step on the calculator. I'll just do them. And what we can do is you know how to compute this on your calculator. I'll run all of these through and I'll put a single value over here for the cumulative, then I'll put the delta x and we'll get the final answer. So let's do it. When I run all of these, I get as my cumulative f of xi right here, cumulative lengths, I get a 8.5771. And then I have to multiply this by 0.2, which is 1 over 5, which is my delta x. And then let's write here our answer, which will be the area below the curve. And it would be 1.71542. Let's be a little neat over here. 1.71542. And it doesn't hurt to check our answer. And it looks good. 1.71542 represents the area below the curve. And you know, what would that be graphically? It would be, if you look down here at this lower corner right here, e to the x function looks like a, and I'm only looking here at the first quadrant. From here 0, 1 is a y-intercept. It would pop out this way, like the exponential curve. And then you're looking at interval 0 to 1, you'd be looking at this area right over here. Right over here. But you know, even though we don't know how to compute integrals, I know how to do it. We can check our answer using this formula right over here, and we can get a true answer. The integral of e to the x, fortunately for this case, happens to be just e to the x, and you're looking at it from 1 and 0, and you run it through. You have one exponent. You have to feed this one value in here, and you have to feed the 0 value in here, and you do the difference. And this is something you learn when we do the direct integration techniques. You learn that. But let me just put this value. The value from this integral process will be the true value. The value here using the midpoint will represent a good approximation of the true value. And that true value ends up being 1.71828. And I'm not taking it to more decimal places, but look at the difference. You have 1.71828. Here I'm getting 1.71542. And then slightly off, but this right here represents the true area. This here represents a good area, a good approximation of the area. And that's one of the benefit of you learning this technique, the Riemann sum technique, is because it's just another way for you to calculate an area or the cumulative effect of the limits, because you know integrals are limit of sums. It's another way for you to calculate limit of sums. And once you know the real integration techniques, you can then decide if you want to keep this technique, the Riemann sum technique, as a part of your tool basket or not. Because once you can do the calculations using integral calculus, then some of these techniques become moot. You don't need to learn them anymore, or you don't need to use them anymore, because you have an easier, more efficient way using integral calculus or integration than versus using this more elaborate technique. But this here represents the true area from integration. This here represents a good approximation of the true area using the Riemann sum process with the midpoint sample values. Let's look at another question. So let's look at this question here. We have f of x equals sine x, and then we have an interval 0 to pi. 0 represents the lower limit, pi represents the upper limit, and we have to calculate R4, Riemann sum number 4. And you know there's a procedure that I'm teaching you all with regards to Riemann sums because they help us understand the concept of integral. The procedure has a certain sequence of steps that I want you all to follow. We start with always finding what the n value is, and here the n value is 4 because it's R4. We're calculating using 4 Riemann sums. If you were to graph it out, you'd be drawing 4 rectangles. Hence the R4 and n equals 4. The next thing we want to do is look at the interval. Delta x is equal to b minus a over n. B is the upper limit, a is the lower limit. Pi minus 0 over 4 is just pi over 4. Very quickly, graphically, just looking here only at the first quadrant, sine x from 0 to pi would look something like this. And you know, at sine of 90, right, at sine of 90, it reaches up to 1, the apex of the sine curve. But we're looking at this interval right over here. You know, we would always want to be using the midpoints. I'm going to draw 4 rectangles, but I'll try to be relatively accurate over here. You see how the top edge of each of these rectangles has a curve going through the midpoint? Well, this is what we're looking at. We're looking at 4 rectangles. If you were to calculate the individual areas of each of these rectangles, 4 rectangles, and add them up, you'd get a relatively good approximation for that area. Well, we're using the Riemann sum formula and technique, and at the end we can confirm it using integration. Though we don't know how to calculate the integration of this type of function, I know how to do it. We can just use that as a test at the end to check that our answer was relatively good. And the procedure we want to use for the Riemann sums has this set of columns. We start with an interval, then we'll designate a sample point, which will be our midpoint, and we'll run it through the function, which will represent our length. What's our interval going to be? It's from 0 to pi, and it's going to be split up into 4 intervals. The first interval will be from 0 to pi over 4, right? The next one will be pi over 4 to pi over 2. You can write intervals in any way you want. I'm just writing it here. Pi over 2 to 3 pi over 4 will be my next interval. And lastly, we'll have 3 pi over 4, because here I'm going up in terms of pi over 4. See, we're going up in terms of pi over 4s. And then 3 pi over 4 to pi represents my fourth interval. You can see everything here is in a difference of a pi over 4. Now we have to just find the midpoints of each of these segments. 0 and pi over 4, the midpoint of 0 plus pi over 4 would be pi over 8. You can add this and divide it by 2. Pi over 4 plus pi over 2, we can bring our calculator and do this. 45 plus 90 divided by 2, I'm getting a 67.5, which in terms of a radian measure would be what? Let's bring it out. It'll be 3 pi over 8. And then look, from pi over 8, 3 pi over 8, we're a difference of 2 pi over 8. So this must be then 5 pi over 8. And then this must right here be 7 pi over 8. And we can check all of this, that I'm not making a mistake over here in terms of my approximations. All of these midpoint intervals are good. So all we would do over here, we would run these values through the function. This would be sine pi over 8. I don't have to write out all the decimals here. This would be sine 3 pi over 8. This would be sine 5 pi over 8. This right here would be sine 7 pi over 8. And you know all of these together would represent the cumulative sum of the lengths. You know the formula. We've written it now many times. Limit as n approaches infinity, right? From the first to the last, to the first to the fourth, or n, f of xi, the cumulative sum of the lengths multiplied by pi over 4, which is your interval. So we have to run all of this through the calculator. I'm going to run all of this through the calculator, add it up and put a value here, then we'll multiply it by pi over 4. It will come up with a numerical value. At the end, then we can use integration or integral calculus to get a true area. Let's put values over here for the angles, because it'll help for the calculator part to expedite it. It'll be good to have these values over here. Now with these values here, we can just do sine 22.5, sine this, sine this, sine this, and add it up, and it'll be very helpful. We end up having here a cumulative length of 2.613125993, which when you multiply by pi over 4, and I do that on my calculator, we get an answer, an area which is 2.05234. And you can think about this sine curve. It's very symmetrical. You have two rectangles here on each side which are equally tall but they're short, and the ones here are equally tall but they're taller than the ones on the sides. Of course my diagram is not drawn to scale, but the first and the fourth rectangle should have exactly the same. Sine of 22.5, sine of 157.5 should be exactly equal, but smaller than sine of 67.5 and sine of 112.5. These will be larger values, but they'd be the same values. These two would be smaller values and they'd be the same values. Anyhow, our area below the curve is 2.052344. I just want to use integral calculus to verify that answer, and I will do so right over here. We're finding from 0 to pi sine x dx, and I know the integral of sine x is a minus cosine x, but we're doing so from pi and 0. So let's come over here and publish this value. I'm going to do cosine of pi minus cosine of 1, and we're of course having this minus outside, and we'll get the value. What we can do is isolate the minus outside. We have cosine of 180, which is a minus 1, minus cosine of 0 is just a 1. We have a minus 2 times a minus 1. You end up having an area under the curve of 2. The only reason why we have this minus over here, this comes here from the direct integration procedure. Anytime you're plugging in an upper limit into your integral or into your antiderivative, we'll talk about all of this, and anytime you're plugging in the lower limit, it's always a difference of the two, hence you have a minus cover, the difference of the two. Anyhow, let's not get too lost in the procedures of integral calculus because we're still focusing on Riemann sums. The true area of the curve here is a 2, but the calculated area using Riemann sums is 2.053234. The only reason why it's off is because I have an n value here of 4. As n would approach infinity, we would actually see this value come and become 2. The beauty of integral calculus is you end up having the true area below the curve or between the curves, or the true sum of the limits from integration of an integral calculus question. You always have a true value. When you use the Riemann sum values or the Riemann sum techniques, you don't have the true value, but when you go with the midpoint, you have a value close to the true value, though it's not exactly equal to the true value. We'll end this video here with this next question, which will be an examination of area between the curves, because I want to show you that the Riemann sums can be used for not just one curve, but it can be used for at least 2 curves, and you can use it even for more than that. I just don't want to be sticking with the mundane concept of just the area below curve, because you can always do area between curves as well. For this last question for the video, we actually have 2 curves over here, so we're looking at an area between the curves. The whole concept of calculating area between curves is a huge part of integral calculus, and I've devoted, and I will devote down the road an entire video or 2 to that subject alone. But here I'm just bringing a future subject into this particular video just for the sake of boosting our confidence with this Riemann sum procedures, that we know we can do more with it than what I've talked about. If you look at this f of x equals x squared and x, in a very exaggerated sense, I'm going to show you the curve looks something like this. Again, I'm exaggerating it here. And you know we have R4, we have to calculate R4, but we're looking at here at the area between the curves. If essentially you're going to draw 4 rectangles, now you're no longer drawing things from the x-axis, you're drawing things or your rectangles from the lower curve to the upper curve, and you could essentially draw 4 rectangles such like this. And you would have to draw them such that you don't have to focus too much on accuracy, but you want to focus here on the idea and the concept. When you're doing areas between the curves and you have not just a single axis to deal with, or you're not arising from an axis like an x-axis or y-axis, but you're arising from a curve and you're using the midpoint sample values, you know midpoints are better than right and left endpoints, then you have to be careful because you have a curve here on the top and a curve on the bottom. Your rectangle must cross, the edge must cross the midpoint from the top, and it must cross the midpoint from the bottom. Do you see how you're crossing the curve from the midpoint of the lower edge and from the midpoint of the top edge? And each of your 4 rectangles, which would demonstrate that if your graph were drawn properly from the lower boundary curve and the upper boundary curve. So these are all things you need to be aware of when you're using Riemann sums, but these are all things we'll talk about in the future. Here I'm just showing you that this Riemann sum procedure can be used to calculate area between curves, and we have 4 rectangles involved, so let's not get too much caught up in this diagrammatic procedure here. The first thing we want to look at is our n value, which we know to be 4. The next thing we want to look at is our interval. I've always kept the interval easy for these questions. There's no need to be more cumbersome or complex with these numbers, because we already know the larger the n value, the more accurate the calculated or approximated value to the true area as you would determine from an integration procedure. The smaller the n value, the less accurate will be your calculated area below the curve or between the curve. Anyhow, our delta x here is b minus a, which is 1 minus 0 over 4, which is 1 over 4, which is just 0.25. And we have a specific set of procedures here we want you to follow. Our interval, then our calculated sample points, which you know will always be midpoints unless otherwise stated, and then f of xi. Here f of xi bears a little notice over here, because our f of xi, or our lengths, are not being determined from an x-axis, they're being determined from one curve to the next. Essentially from a lower curve, which is your x square. Remember, the graph is like this. You have an x square and then you have an x. From a lower curve to the upper curve. We'll talk about this in a future video, but for right now, take it for granted that our calculation here will be upper curve minus the lower curve. The top boundary curve minus the lower boundary curve. The top boundary curve is x, the lower boundary curve is x squared. So this is the formula through which the procedure will run through. Because we don't have a single function here, we have two functions. But the upper function is the x function. See, the upper curve is the y equals x. The lower function is y equals x squared. After a certain point, the x squared goes out of bounds because it's exponential, whereas the y equals x is a linear. But initially from 0 to 1 interval, the y equals x is a higher curve and y equals x squared is a lower curve. After 1, the x squared becomes a higher curve and the y equals x becomes a lower curve. But that's not relevant here because we're not going beyond the interval 0 to 1. We're not going beyond that interval. So what are our intervals? Each interval is 0.25 and we're going from 0 to 1. So we have 0 to 0.25 is the first interval. The next is 0.25 to 0.5. My next interval is 0.5 to 0.75. And then my last interval is from 0.75 to 1. And now we have to find the middle. The middle of 0 and 0.25 is 0.125. The middle of 0.25 and 0.5 is 0.375. The middle of this is 0.625. And this right here would be 0.875. And so we're running 0.125 through this formula right here. 0.125 minus 0.125 square. Here I'll start posting in decimal values. Remember, this right here is our f of xi right here. X minus x squared. So we'll do 0.125 minus 0.125 square, and I'm going to put in these values. I get 0.109375, and in the end we can use integration procedure to actually publish a true value, and we can compare our calculated value to the true value. 0.375 will go through this formula right over here, x minus x squared, because we have x here on the top and we have x squared on the bottom from this interval 0 to 1. Here I get 0.234375. I have 0.234375, same, because we're having rectangles here pop up with the same magnitude in terms of height. That's 2.875. I have a feeling it'll be the same as this. It's 0.109375. Let's run it through our formula. Limit as n approaches infinity, and we should write here R4 equals, from I equals 1 to n, we'll have the cumulative effect, or the sum of these lengths. All of these cumulative lengths will be added up and they'll be multiplied by delta x, and we'll publish the value over here. Let's add all of this and multiply by 0.25. I'm getting a value of 0.171875 as representing the area between the curve x and x squared. Alright, so this is my calculated value using the midpoints and using the scheme here. Now what we have to do is actually do the integration. We don't have to do it, I'm just doing it for the purpose of this video to verify how close I am to the true representation. This is something you learn in the future, but the area for the region between these two curves will be the top curve minus the lower curve, and from the interval 0 to 1 area with regards to x, area of x is equal to the top curve x minus the lower curve, which is x squared and dx. If you were to run this through the integration procedure, you'll have x squared over 2 minus x cubed over 3. Don't worry about all of this. This is all stuff we'll learn. From upper limit to lower limit, we'll have 1 over 2 minus 1 over 3, and what do we get? 1 divided by 2 minus 1 divided by 3, I get 0.1666, which is basically 1 over 6. This 1 over 6 represents the true area for the region between the curves right here, x and x squared from 0 to 1. And I'm getting a 0.171875, so I'm slightly off, but that's fine. I'm off simply because I have an n value of 4. Had I probably taken this to a much larger number, this value would have trimmed down and gone smaller and smaller and come towards 1 over 6. 1 over 6 represents the true and the accurate value for the area between the curves. This just is an approximation of it. But had I used the right endpoints or the left endpoints, I would be significantly away from this true value right here. Remember again, integration procedures will give you the true value for the area between the curves or below the curve. The Riemann sums will give you just an approximation, a relatively good approximation if you use the midpoints. Pretty much that's it for this video. I hope you enjoyed it. Hopefully it makes the Riemann sum concept even more clear. In the future 2 videos, when we're still talking about Riemann sums, we'll be looking at different aspects of Riemann sums. So it'll be slightly divergent from what we're talking about here, but the main concepts will still be the same, but you'll see some new ideas and concepts with regards to those Riemann sums. Well, thank you for watching this video. Have a nice day. Bye.